In this video, we'll be looking at how to use trigonometric ratios of sine, cosine and tangent with right-angled triangles in order to calculate missing angles and lengths. Before you start this video, I would suggest making sure that you're happy with rearranging equations by watching the rearranging equations video from earlier in this series. Here we have a right-angled triangle as designated by the square in the corner here. It's always worth checking that this is marked or stated in the question, and it shouldn't be assumed. We have an angle which we've marked with the Greek letter of theta, which is a common symbol for a missing angle in a trigonometric question. In order to use trigonometry to solve for the angles or lengths of a right-angled triangle, we need to ensure we label the sides according to the angle that we are trying to use or find. The side that faces the angle is called the opposite side, as it's opposite the angle that we're using or finding. The longest side, which faces the right angle, is known as the hypotenuse. The remaining side is adjacent, and this is the one that runs adjacent to the angle. We tend to label these with O, H and A. And I tend to circle these labels to stop the O being confused with a 0. Now we've labelled the side, we can consider the trigonometric ratio and how to use them. There are many mnemonics that help you remember this, but I tend to use the one that sounds like a Hawaiian volcano, SOH-CAH-TOA. This tells us which sides are used with which ratio, and it can be expanded to show how they are used like this. Sine theta equals opposite over hypotenuse. Cos theta equals the adjacent over the hypotenuse, and tan theta equals the opposite over adjacent. Before we go any further to use these in our equations, let's see how we can find these ratios on a calculator, and also how to create the inverse of these ratios, which we'll be using later in this video. To find sine, or sin as it's abbreviated on the calculator, you simply press this button. To find cosine, or cos, you press this button on the calculator. To find tangent, or tan as it's abbreviated, we press this button on the calculator. Now, in order to get the inverse of these ratios, what we'll need to do is press the shift button and then the button that it refers to. This will give us the ratio with a power of -1, which you can see written in orange above their buttons. Let's look at how that is used when rearranging the equation to find an angle. Here we have a right-angled triangle in which we wish to find the angle. We have two sides whose lengths are 9 centimeters and 15 centimeters. As the 9 centimeter side is opposite the angle, we label this as O. As the 15 centimeters is the hypotenuse, we label it as H. Now we recall our mnemonic of SOH-CAH-TOA to enable us to check which one to use. As I have the opposite and the hypotenuse, I'll be using sine to find the angle, as sine theta equals opposite over hypotenuse. We can now substitute the known values in for our variables of O and H, and we can write sin theta equals 9 over 15. Now we need to move the sine over to the other side to get theta on its own. Normally we'd divide by both sides as we're multiplying by sine, but we can't do that with a trigonometric ratio, so we use the inverse and write it as theta equals the inverse of sine, open brackets, 9 over 15, close brackets. If we type this into the calculator using the shift key to get the inverse, we'll get the answer of 36.86. And I'm giving the answer to one decimal place. I'm only interested in the second decimal place, therefore, to get the rounding correct, and I get the answer of 36.9 degrees for theta. Here we have another right-angled triangle. This time we have the opposite and adjacent sides, and we can label them O and A. Again, our mnemonic is SOH-CAH-TOA, and we have the opposite and adjacent sides. So we'll use tangent, so tan theta equals opposite over adjacent. Once we substitute in our values for our variables, we get tan theta equals 9 over 12. And then use the inverse of tan to get theta on its own. We then get theta equals the inverse of tan, open brackets, 9 over 12, close brackets, and after we put that into the calculator, it also gives us 36.86. As this can be rounded to 36.9, which is the same answer as the previous example. Now, let's look at how to go about finding a side if you know the angle and one of the sides. Here, we're trying to find x, which is the side opposite the angle, so we'll label it O. The side that we know is 12 centimetres, and we can label this as A as it's the adjacent side. Again, a reminder, the mnemonic is SOH-CAH-TOA. As we know the adjacent, and we need to find the opposite, we're going to use tangent, because tan theta equals opposite over adjacent. We can substitute in the values for the variables and get tan 32 equals x over 12. We always want to get the variable on its own, so we multiply both sides by 12 to get 12 times tan 32 equals x. Let me show you what happens when we put that into the calculator. This gives us 7.49 to equal x. We're then going to round it to one decimal place, and it gives us the length of 7.5 centimetres. Now let's see how we deal with an unknown side being the denominator of the fraction. Here, we're trying to find the hypotenuse, which is x. We have the adjacent side, which is 12, and the angle, which is 32 degrees. Our mnemonic, SOH-CAH-TOA, and as we're using the adjacent and the hypotenuse, we'll use cos, which we can write as cos theta equals adjacent over hypotenuse. Once we substitute in the values for the variables, we get cos 32 equals 12 over x. There is a shortcut here, but let me show you the work behind it. To get x on its own, we're going to first multiply both sides by x to get x times cos 32 equals 12, and then divide both sides by cos 32 to get x on its own equals 12 over cos 32. What we've done is simply swap the variable x for the cos 32. And those are the steps you can jump to get straight here from the original setup. Let me show you what this looks like when I put it into the calculator. So we'll set it as 12 over cos 32, close the brackets and press equals, and we get 14.15. So the calculator shows us that we get 14.15, so we can say that x equals 14.2 to one decimal place. Next, let's look at how we'd use that in an exam style question. In this question, a decorator leans his ladder up against a wall. To be safe, the ladder must be between 70 and 80 degrees to the ground. And we're asked to calculate whether this ladder is safe. Firstly, I recognise that I want to use trigonometry as I've got two sides and I'm trying to find an angle. Next, I can label the sides, with 8.2 being opposite the angle I'm trying to find, and 2.1 being adjacent to it. As I'm using the opposite and adjacent, I'm going to use the tangent ratio and write it as tan x equals 8.2 over 2.1. I'll get x on its own by multiplying both sides by the inverse of tan to get x equals the inverse of tan, open brackets, 8.2 divided by 2.1, close brackets. If we put this into the calculator, we find that the angle is 75.63. As this would mean that the ladder is roughly 76 degrees, we can say that the ladder is safe. Here, we're asked to calculate the length of the ladder. And this brings us to a question of choice over the processes that we can use to find things in right-angled triangles. Here we have two known sides and an angle. Let's use the opposite side to the angle of 8.2 to calculate this, and recognise that we're looking to calculate the hypotenuse in this case, as that's the side that the ladder forms in our right-angled triangle. As we're using the opposite side and trying to find the hypotenuse, we'll use sine and substitute in the values to get sine 75.63 equals 8.2 over h, because we're trying to find the hypotenuse. We can swap these to get h equals 8.2 over sine 75.63, and once we put that into the calculator, we get 8.46, or 8.5 rounded to 1 decimal place. We can now state that the ladder is 8.5 meters long. Now, if you've watched the Pythagoras video or used Pythagoras before, you may have noticed that we can also use Pythagoras to solve this question. We have two known sides in this right angle triangle and can easily calculate the third by finding the square root of a squared plus b squared, or the square root of 2.1 squared plus 8.2 squared. If we put this into the calculator, we can find that the length is the same, and we still get 8.46 to the same degree of accuracy. You can decide which method you want to use in these questions, but it also works as a good double check should you choose to. Here we have two right angled triangles placed together. We're asked to calculate the length of side BD, which is the hypotenuse on the larger triangle. In order to get this, we're going to need one of the other two sides. As BC is adjacent and shared with the smaller triangle, I'll probably use that. I'll label the adjacent on this side. To find that, I can use the measurements in the other triangle, as we have an angle and one of the sides of this right angle triangle. The 6.5 meters is the adjacent, and I'll label that as A, and BC is the opposite in this triangle, and I'll label it as O. As we're trying to calculate the opposite side in the smaller triangle and we have the adjacent, we'll use tangent or tan. And we'll substitute in the values to write it as tan 55 equals BC over 6.5. We can then multiply both sides by 6.5 to get 6.5 times tan 55, which we can put into the calculator and get 9.282. A quick note here that if we want to use this number in the next stage, we should leave it on the calculator, as rounding part way through the calculation can cause accuracy issues. We can recall this number using the ANS button as long as we don't use the calculator in between. In the larger triangle, to find BD, we'll use cos, as we're using side BC, which is now the adjacent, to calculate BD, which is the hypotenuse. So we can substitute and write cos 36 equals 9.28, or the ANS button if you have it still as the last thing on your calculator, over BD. We can swap these to get BD equals 9.282 over cos 36 to get the answer of 11.45, or 11.5 to 1 decimal place. So we can state that the answer to BD is 11.5 meters in length to 1 decimal place. In this video, we looked at how to use trigonometric ratios of sine, cosine and tangent and apply them to find the angles and lengths in right angle triangles. In the next video, we'll look at calculating area and perimeter of circles, as well as learning what parts of a circle are called. I'll see you then.